All right. So today's is about Chubby integrals. Let's go over double integral first. Okay. Suppose you have you're given suppose you're given a domain in dimension 2, right? That's a D. Okay. Then you have a double integral, right? Okay. Now, how to set up an iterated integral for this? Okay. So there are a couple ways to do. One is if you want to put the x outside, okay, then this is always a fixed interval, okay? So it's nothing to do with any variables, the one outside, okay? Then for each x, okay, for each x, you draw the vertical line, and then for that x, you have to determine the y variable, okay? The y variable, if it's as a lower bound depends on x, will be, let's say h1x, the upper bound h2x, okay? For each x between b and a, then you have the lower bound, then have an upper bound, and this is a function dy, okay? Now, similarly, this is how do we set up. Otherwise, see some students, if I ask you to change the order of the double integral, some students just change the integral without understanding how do we set up the iterative integrals. That was when I was grading the test. There are indeed a couple of students doing that. Even you claim you already spent 3 days to study, I don't know how to say it, okay? You did not pay attention to the iterative integrals. So this is not going to be, let me repeat again, it's not going to be h of x. Okay, that if you write in this, you totally don't understand double integrals and the iterative integrals. Okay, so it's harder to give you any partial credits if you do that. We never have an integrals like that. Okay. Okay. So now we want to exchange the order. You still use the same D, right? And this is a C and that's a D, the upper bound for C and D. You take an arbitrary point Y, okay? And then you have integral from C to D and then dy. Okay, it's all side. So you draw a horizontal line. Along this line, Y is fixed, but the X is not fixed. So for each Y between C and D, then you should get lower bound for X, upper bound for Y. But both, this is a E, and we can use a G, okay? So this is a G of Y, the lower bound, G of 2Y, depends on Y, because upper bound, lower bound depends on Y, right? So this is okay. Then you have a G1Y, G2Y, because sometimes G2 is a constant, okay, it's possible. So this is the most general case. So that's why you have exchange the order of the iterative integrals. Okay, so that's how do we solve the problem. Okay, so example. Okay, so here's the example. Okay, and this is a line. Okay, y equals x, and this is a parabola. Okay, so you are given this 2. Okay, this is a D. Okay, and here's a double integral. Set up 2 iterative integrals for this double integral. Right? How do you do that? Clearly, see, the first one is for the dx, right? So x clearly from 0 to 1. So from 0 to 1. Then for each x, I really want you to write down this kind of sentence here. Okay. Otherwise, especially for those students who made mistakes on the iterative integrals. Okay. You needed to write down this sentence when you do the homework. Okay. For each x, and what is you draw the picture, okay, repeatedly. I have to say that. You cannot just, without looking at picture, set up an iterative integral. For each x, what are the values for the y, okay? The value for the y, the upper bound is determined by the strict line. So when x is fixed, the upper bound for y is x, okay? No, the upper bound must depend on x, okay? Lower bound must depend on x because x is fixed. The lower bound is x squared, okay? Because this is from the parabola. So that's, okay? Okay. Now, if you want to, but I have to say that it is not going to be, it's not going to be this integral, okay? This does not make sense. If you write in this, means you totally don't understand the iterative integrals, okay? You cannot just change the order of the integrals or including, exchange the integrals, including the same intervals, okay? It's not, okay? So, so let's repeat the same picture here, okay? Now this time we're going to put y outside, okay? The y variable, look at this. The upper bound will be still 1, lower bound for 0, so 0, 1, okay? Then for each y, let me repeat again. For each y, you get, yeah, for each y between 0 and 1, okay? Then for each y between 0 and 1, and you look at the points on this horizontal line, and there's x cannot be arbitrary. The lower bound for x is determined by the strict line. The strict line is going to be x is going to be equal to y, so it's y. Okay, this must be a function of y. Okay, the upper bound x is determined by y also because y equals x squared, x is a square y. Okay, so it's a square y. Okay, so okay, if you understand those two examples, these examples, you should be able to solve all the problems about iterative integrals. There are about 5 students did not know how to set up iterative integrals before they took the test. Okay, at least they did not spend time. In my opinion, they did not spend enough time to practice over this material. Okay, otherwise, why there was no idea, set up or mistakes. The idea is very simple here. Okay, and if you look at my lecture notes, okay, and also watch the videos, this is what I'm repeatedly saying that many times. I did not see the sentence for each y between 0 and 1, x is between like that. I did not see that sentence. That means you did not catch the point. Okay. Okay. You have your own idea to solve the problem, but you should solve it, right? But you made mistakes. So I want to see the picture and that sentence. That means you do get idea how to set up integrals. Okay. All right. The Chubby integrals. The so-called Chubby integrals, we live in 3-dimensional space. We also, we studied the integrals, 1-dimensional integrals, and then we have a 2-dimensional integrals, right? And then we have to go on to 3-dimensional integrals. The first, the simple case is the domain, the region. Okay, I'm going to use this region. It has it's a rectangular box. Okay, so this is the domain. It's in the space. That's a special case here, right? Okay, this is our domain. Okay, the domain is 3-dimensional space. Okay, the function is defined. It depends on 3 variables. Okay, and the triple integral of this function. Okay, we use a dv. Okay, this is how do we do that? This is actually still use the definition still use the limit of a Riemann sum, okay? Limit of the Riemann sum. So what I do is ijk equals 1, and f of I star, y I star, z I star, and here's delta xy, delta j, and the delta zk, okay? Now what does that mean? And here, the limit that should, okay, so I divide this cube into many smaller cubes, okay? So the inside, there's a smaller cube, okay? This cube is here's delta xi, and this is a delta, this is delta xi, this will be delta yj, and this is delta, this height is delta zk. So this little cube, the product of those three terms is going to be the volume, okay? So this is delta v, okay, ijk. So it's a volume of this, the product of the three terms. And xi star yj star zk star is some point here inside, read and pick up. So the value of the function times the volume of this little cube, you add them together called a Riemann sum. And if the Riemann sum approaches some number, okay, when those cubes are getting smaller and smaller, smaller means all the sides are getting shorter and shorter. Then if it has a limit, then this limit is called the Chubby integral of the function, okay? Of course, we are not going to use this to find to evaluate the Chubby integral because it's so difficult to come, okay? But what Riemann did, Riemann says that Riemann's result, again, okay, Riemann's result is if f is continuous on this region D, then the Chubby integral exists. Okay, exists. And furthermore, okay, one can also show that if yeah, this is a cube, okay? Okay, now you can, then if we have a irregular solid, not just the cube, okay? Then how do we find the Chubby integral? So we here, you see, if we have like a potato, like this kind of solid, okay, okay, in the space, this is my region. The function, yeah, the function here, we assume that f is continuous on this region R, okay? That's the first condition. Second condition, the boundary, okay? This is a boundary, okay? Is a nice, okay? Nice, good means consisting of smooth surfaces. It's not necessarily completely smooth everywhere. Maybe like maybe looks like yeah, looks like that. Okay, so the top was smooth, bottom smooth, but they grew together along the circle, something like that. It could be. It also could be. Yeah, it's harder to draw it. It could be like that, something like that. Okay. Okay. So this type of consists of smooth surfaces, but it's good enough. That's not smooth along the edges, but it's smooth in each. Each surface is smooth. Okay. They grew together, something like that. Then we extend, yeah, this function. Yeah, let me define this function, f(x, y, z). if this is a point in R, otherwise you send if X, Y, Z is not in R, okay, outside, then this function is integrable on the cube cover this, okay? So let me draw the larger cube, okay? So this is a larger cube. An arbitrary cube cover that, okay? This is a box, it's not a cube, okay? This is called R2, okay? Then this function is integrable. Integral means the limit exists. Any we call it prism, okay? This R2 A, B, C, D, R, S, T containing this R, okay? And the value is independent of how big of the box. It doesn't matter because you see the function is a smooth, with 0 always. So outside, if you even enlarge the R2, yeah, even enlarge the R2, you do not change the value. That's reasonable because here the function here is F2 is 0, and here F2 is F, right? So you enlarge the domain, but it does not have any impact on the value. Okay, so in other words, this triple integral. So we define this triple integral. Okay, to be the triple integral over this rectangular box, okay, containing that up. Okay, that is. Then the next step is how to solve the problem using iterative integrals. Okay, the forbidden theorem is still true for above f. Okay, we can evaluate using triple iterated integrals. Okay, so how do we do that? I just give you an example. Okay, so we can the idea is, okay, so this is for example, there are many ways to evaluate. Okay, so this is going to be, yeah, we have the forbidden theorem. Okay, for the above function f and r. Okay, this triple integral can be evaluated using iterated integrals. There are many versions of iterated integrals. I just choose one of them. Okay, this is going to be like from A to B. Okay, because you R2 that, right? And that is dx, and that will be d. Okay, let's say I put a d here, f to the xy dA. Okay, what is d? D is CD cross IS. Okay, then you can continue, right? You can continue. Okay, so you can continue the three layers here, right? IS, F to the X, Z, and that would be DZ, DY, and DX. Okay, it's called iterated integrals. On each of them, I keep F to that because F will be 0 outside some intervals. Then you replace IS by functions. Okay, so this is also can be viewed, yeah, this is also this also can be, this part can be combined into the double integrals. Okay, this is going to be, let's say, d. Let me put it dx, yeah, because this is x is determinant. Okay, this could be, yeah, this is interval. Let me, yeah, I'm not going to use d here, just to use the interval directly. Okay, the domain. So this will be AB class CD. That's the domain. Okay. So dA is going to be dx dy. Okay. So there are many ways to evaluate the Chubby integral using iterative integrals. Okay. Let's look at some examples.
Professor?
Yes.
I'm looking at the book here, and it's saying that there's because you use this potato example, right?
Yeah.
So there's like different shapes, like kind of
yeah, this is the most general
shape.
shape. You know, this is the most general one.
So it breaks it down into two different types. There's type 1 plane region and type 2 plane region. And I really don't understand what type 1 means and what type 2 means.
Well, they're just trying to classify the regions in two different forms, but most of them we will only consider those type of regions. But let's look at some examples, and then we see. I don't pay attention to the classification of the type 1 region, type 2 regions. Okay, so all we needed to know is how do we cut this potato to use iterative integrals to evaluate. Okay, so let's go through some examples, and at the end we can, yeah, you can name, you can name the regions in the use your own language, it doesn't matter. Okay, so here's the first problem I'm going to discuss. Okay, this is I is bounded by equations inequality, and then another one z is greater than 1, less greater than 0, less than 1. Okay, so in this case, I think I'm going to pay more attention to set up the iterative integrals. Okay, so I'm not going to use a specific function to solve it. So set up the iterative integral for this triple integral. Okay, so here's the domain. Here's the domain R. Okay, this is the domain R, the cylinder. Okay, and these are this is 1. These are from 0 to 1, and x squared plus y squared is less than or equal to 1. So this is a solid. It's a cylinder. Okay, this is my R. Okay. Okay. So we try to set up the iterative integral for this one. Now, there are many ways to do that, right? So you can put it in the box. You can say this is inside the box. Okay, let's begin with the box. Okay, an arbitrary box. Okay, so this box could be, the height is 1, but could be a square. Yeah. So the box could be R2, that is going to be 0, negative 1, right? To positive 1, negative 1 to positive 1, and 0 and 1, for example. This is a box, square based. Okay, box, you can cover this, yeah, include this whole cylinder. So the question is, how do we, yeah, so this F2 the X, Y, Z, and if in the future we're going to skip that steps. All right, for this box, okay, what I'm going to do is, I can use this double integral here. Okay, that will be from -1 to +1. Okay, this is square. That's a square. Okay, then here it's from 0 to 1. Okay, f2 dot x, y, z, dz, and dA. Okay. So I cannot remove the f2 dot yet. However,
I thought you wrote -1.
yeah, it's from negative to positive one. Okay. No, this is you see, the cylinder is on the circle, but I cover the circle using square. So that's why it's from -1 to +1. Okay.
And I'm seeing from 0 to 1. That's why I'm confused.
No, I mean the height. You see the cylinder, z is already
Oh, I see. Okay,
from
perfect.
0 to 1. Z is from 0 to 1. All right. So I cannot remove the 2 dot yet, f2 dot. So I can change this to the disk D. Okay, this is my D. So I can put it back D here again. Now, once I put a D, then because all sides of D for X, Y, all sides of D, this is going to be 0. So then I can change the function to the original function. Okay, then dA. Okay, so if this is a disk, then I can use the polar coordinates to evaluate the integral. So this triple integral right now can be evaluated using this iterated integral. One is a double integral, other one is just single integral. Okay, so so it depends. Okay, another way you can do is you want to use a variable z first. Then how do we? Yeah, you can this because the triple integral for the triple integral on the rectangular box also you can always exchange the orders. Okay, this will be dz. Okay, and here is still from -1 to +1, and this is a fxyz 2 dot, and then this is a dA. dA is the dx dy. Okay, all right. So all right. You can always, yeah, because it's a box, you can always interchange the freely. You can interchange the integrals. All right, now be careful here. For the f2 dot over this interval, okay, let's look at this. And for arbitrary z, okay, for arbitrary fixed z, and this is my square, it's here. Okay, this is my square, it's here. For the z, xy is not going to be, yeah, xy, point xy here, xyz, right? xyz. So xy, because this is in this picture, yeah, this special solid. So here's the xy, okay, at the bottom. So for xy inside the disk D, the function f2 that equals f, but outside it's 0. So that's why you can also use this D. D is x squared plus y squared less than equal 1. And then that's just f. So for this example, you basically can change this two integrals. One is double integral, other one is a single integral. You can exchange it, no problem. Okay. And there are many ways to do that. You can begin with a single integral, then have double integral. And the double integral also can become iterative integrals. You can change it to the iterative integrals. Okay, so this two iterative integrals, one is the double integral, yeah, that's two integrals. And you can also, if you use polar coordinates, and this could be, yeah, this could be from 0 to 2 pi, from 0 to 1. And here's f, and x is going to be r cosine theta, y is r sine theta, and this is z, and d, here's r, dr d theta. Okay, then dz. Okay, so inside you can evaluate using polar coordinates. Okay, because
That's
this
that
is
third term for z is r theta, correct?
the third
For
term.
for z.
So for the z is just z. We cannot change it. We not only change it for x and y.
Because we've already defined z as our height,
These are from 0 to 1. Yeah.
right?
So here, x is going to be r cosine theta, y equals r sine theta. We just focus on this double integral and change the coordinates. We do not touch the z variable. Okay. Yeah. Okay. All right. So now here's the next one. The next one is the next one is a ball. Okay. So the domain is going to be.
What would be the answer for the first one, Professor?
For the first one, the answer is just to set up iterating integrals for this triple integral. So you have one, we have two. Either one is okay. Yeah. My question is, without question, can I have answer, right? My question is set up the iterating integrals for these triple integrals. Okay. So I have two iterating integrals. Yeah, I have two iterating integrals for this. Okay. Actually, for some problems, you can have six iterating integrals, okay? Because these three integrals can be three factorial many orders, okay? X, Y, Z, Y, X, Z, X, Z, Y, So, but I don't want to go to the last step. I just say one is a single integral, other one is double integral. Okay, in that case, even we still have many options. Okay, for some problems. Okay, so here I just get the one single integral is using z variable. The other double integrals are using xy variables. Okay, but for the sphere, you have what is it? This is let's look at the sphere. Okay. Yeah, I'm going to find the problem. All right, so this is a ball, okay. Okay, and you have a function. This is my r. Okay, so you have a function x, y, z on that. So then you first, this is a triple integral. Let's try.
Are we just setting this up?
Yeah, we're trying to, set up the iterating integrals for these triple integrals. Okay. Yeah, set up a written integral. Okay, it's also integrals for this tree. So there are many iterated integrals you can set up. Okay, so you can use this is because it's rounded. Okay, so this part d is going to be x squared plus y squared less than or equal to 1. Okay.
Is this a sphere or a ball?
It's a sphere. This is a ball, yeah. The domain is the region is a ball. Ball means is a solid, okay? Enclosed by the sphere. Sphere is a two-dimensional surface. Okay, so this is a ball. So what I'm going to do is, I'm not going to draw the rectangle box right now. Okay, I'll skip that step. So what I'm trying to do is, I'm trying to do is this will be the double integral, okay, over the d, and then the single integral with respect to z. Now, how to do that? Okay, you project this solid to the d. Okay, so it's very similar to the one I did for the single integral for double integrals. So here's my sentence. For each point x, y in D, okay? For each point x and y in D, I take a point, okay? And then I draw a vertical line. So those lines, occupy the whole solid, okay? Yeah, occupy the whole ball. So the z variable, there's the upper bound and lower bound for each fixed and y. So upper bound is going to be 1 minus square, 1 minus square, square root of 1 minus square minus y square. The lower bound is negative, square root of 1 minus x square minus y square. So that is the upper bound, lower bound. So the d is fixed. Okay, it's a disk, unit disk. So this is going to be okay, and then here's a function x, y, z. Okay, so this is then you can deal with the double integrals, because once you evaluate the integral inside, then you get a double integral. Okay, then you get a double integral. All right. Okay. Now, can we set up another integral? Outside is a single integral, inside is a double integral. You cannot just switch the order. Okay. This is not going to be. Let me again. It's not going to be because the integral outside shouldn't depend on any variables. Okay. So this is not going to be d is x squared plus y squared less than 1. This does not make any sense. If I wanted to exchange the order, okay, this does not make any sense, because when you evaluate the double integral inside, you will get a function for z. Okay, and then you evaluate this again, you get a function of x, y again. Now let's get a function of x, y again. So you should get a number, nothing to do with x and y. Okay, so how do we exchange all of these integrals? Okay, we go back to the sphere, the ball. Okay, this time so the upper bound for the z is going to be negative 1, and the lower bound for the z is y, right? So this is x, this is y, z. Okay, so take arbitrary point z.
Professor, I know that you're jumping to the other way to think of it, right? But can you go back and explain what the specific bounds for x and what the specific bounds for y would be?
No,
in your previous example.
No, there's you see, the bound for x and y together, it's double integral, is 1, x squared plus y squared less than equal 1. So this is a double integral over that disk. So when you say the bound, it means the boundary of that disk, okay, which is a circle.
So I would, for each, when you're evaluating this, right? So if you
first of all, you evaluate the inside integral with respect to z, then you get a function of x and y, then you get a double integral over the disk.
correct.
Then the step is depending on which method you use. Typically, it's using polar coordinates because it's disk.
And then you break it down into polar coordinates.
The point is you try to use some lines to cut.
Do you mind continuing that example, because that would really help me?
Yeah, I'm using the same example, but I'm going to do a different way to set up iterated integrals right now. So this is the same function, this same ball. Okay, so what I'm trying to do is I'm trying to set up an integral, something like that. Okay, and this is going to be double integral and dA. Okay, so I'm trying to do like that. The question is how to do this. Okay, this dA is a dy, dx, dy. Okay, okay. I want to do this. So for each z between 1 and -1, because look at this, right? The lower bound is negative and upper bound. Okay, so how can I cut this ball? I use a horizontal plane to cut through. So this is my d, but depends on z. Okay. Okay. So that is going to be, it's from -1 to +1. Okay, it's the same function. Okay, this is integral of a dz, and this is a fx yz. Okay, so but that dz, d sub z, it depends on the value of z. Okay, it's not going to be fixed. Okay, so this is described by xy. Okay, x squared plus y squared plus z squared for any point inside the ball is less than or equal to 1. So for the point on this disk, it's less than or equal to 1 minus z squared. Okay, so the answer is yeah, that's the dz. dz is actually two variables determined by this inequality. Okay, it depends on z. So my double integral right now, it's going to be -1 to +1, and yeah, you can say x squared plus y squared less than or equal to minus z squared, and here's x, y, z, dA, and dz. Okay, and when you evaluate this is the integral. The radius is the square root of 1 minus z squared. Okay. Okay. For fixed z, you evaluate this double integral over a smaller disk. It's not a unit disk, and depends on value of z. Okay. So this is
if I can try and summarize what you're saying here. So for there's two ways to look at these types of triple integral problems. The way that you're telling us right now is where we can take a slice of z, where z is variable, right? Yeah. And the other way to do it is to take a slice of xy, and then where z is a fixed constant, right? Am I getting that correctly?
The other one is is z. So there's two different ways to, you see, we describe the ball. You know, here we use a vertical lines only. So those are the vertical lines. Depends on the point in the disk. When the point on the disk changes, then all the vertical lines occupy this whole ball. Okay, and here we use a disks. Okay, we use a disks to occupy the whole ball. Okay, so this disks depends on the parameter, depends on z. Okay, that's why the integral, also integrals dz. You know, you fix the z, and you get a disk. You have to describe the disk, how the disk changes, the size changes. So, okay, and for the cylinder, we do this. We can do this. We can do the same way. Okay, for the cylinder problem, for the cylinder problem, we can do the same way. Okay, if I change the problem to the cylinder, okay, so this is cylinder. I go back to this problem again, and here x squared plus y squared less than or equal to 1, and z is between 0 and 1, and actually a little bit easier than this. Okay, and here's the cylinder. Okay, so how do you do this problem? You can set up iterated integral in two different ways. The first one is for you want to set up in the last variable will be z. Okay, so there's a iterative integral. Sorry, the triple integrals. is going to be the last integral. It should be z. Okay, and these are between 0 and 1. Okay. So for each z between 0 and 1, because the upper bound is 1, lower bound is 0. So for each z, you get a cross section. That is my dz. Okay, but this dz actually is independent of z. Okay, dz is just actually is just x and y, and x squared plus y squared less than or equal to 1. Okay, so it's independent of z. So then this will be the double integral of z and fx yz and dA. Okay, and so z since z is independent, dz, yeah, this domain is independent. The domain actually is from here, right? So this is same d. Okay, so this can be removed. It's from 0 to 1. You can simply write x squared plus y squared less than or equal to 1 fx y z. Okay, you can make it simpler. Okay, so this is an iterated integral for that integral over the cylinder. Okay. And now let's use let's look at different type of a region in the space. Okay. Then this time I'm going to evaluate integrals. Okay. Here's the Chubby integral. I think that's problem number 12, and that's domain E sine y dv. Okay. Now let's describe y. Describe r. R lines below y z equals x and above the triangular region was vertices. Okay, 0, 0, 0, pi 0, 0, and 0, pi 0. Okay. Okay, let's draw the pictures. This is a difficult part, right? So 3D picture. Although we live in a 3-dimensional space, it's harder to draw the 3-dimensional picture. Yeah, my research area is a high-dimensional space. It's harder to imagine, right? A 4-dimensional, 5-dimensional space. So my subject is geometry. All right, so we can only see the shadow of the high-dimensional object in 3-dimensional space. Okay, when we want to visualize it, we have to find the shadow here. Okay, so this is a picture. Okay, it's YZ. Okay, so vertex. So this is a x 1 point pi. So this is a triangle. That's my D. Okay, this is a triangle. Now z equals x. What does it mean z equals x? Z equals x is in the xz plane is just a line, something like that. But there's independent of the y variable. So you have a plane. So this is a plane. Okay. This is a plane, looks like that. Okay. This is a plane. Okay. And we only consider the portion under this plane. So it's harder to draw it. Yeah. I think it looks like that. Okay, so this is a piece. About this, right? Can you see that? It's not easy to draw, okay? Okay, so that is a piece. So region is under that, so it's going to be like this. I draw the vertical line, and behind that, that's another line. Okay, so yeah. The question is how do we set up the iterated integrals? So what I'm trying to do is I'm going to use a vertical line to occupy this whole region. So this Chubby integral, okay, sine y dv, I'm going to set up integrals like this. Okay, and that will be dA, and this should be dz. Okay. So these are triangle, okay? These are the triangular region, okay? Let D be the triangle region, okay? These are triangle region for each point in D. This is triangular region, okay? Triangle region in the XY plane. Okay. The Z actually is between the lower bound for this 0. The upper bound, it's already given. It's determined a plane, so it's less than x. Okay, right? Yeah, the plane is z equals x, right? So that if you fix the point x, y, if you want a 3-dimensional space, also put the coordinate 0 in the first component. And then you look at all the points on this vertical line. What is the lower bound for z? What is the upper bound for z? Lower bound for z is 0, upper bound for z is x. All right, so z is going to be from 0 to x sine y, okay? All right, and then you evaluate, right? So sine y is independent of z, so it's going to be x sine y, and you get double integral. So now you focus on the double integral. Okay, focus on double integral. And this is a pi z. I think this is 0 pi. Okay.
Professor, why wouldn't you get, we're doing it with respect to z, right? So why wouldn't you get z sine y? Or could you? It's just because z also equals x, you're using x.
Why is z sine y?
If we're evaluating the integral from 0 to x of sine of y with respect to z, dz, right? Wouldn't we get z sine y with the to get the bounds 0 to
okay.
x?
Because this is a constant, okay? So when this is constant independent of z, so the entire derivative will be z sine y, but evaluate at the 2 endpoints.
Yes.
So
That's
then
what I'm saying.
by
and then you plug in your x. That's what you did. You just skip that
right.
step. Okay. That's what I needed to know.
Yeah.
Thank you.
All right, so now it's a double integral. So question is, how do you set up a double integral? It's the same idea. And you can use any variable, okay? You can use x variable, you can use a y variable. Let me use both variable, okay? It's the same, okay? This is if you want to use a x variable outside, okay? Then you have to say for this equation here is a x plus y equals pi, I think, yeah. So for each x between 0 and pi, the y value use the horizontal lines, right? The y value is between 0 and pi minus x, okay? So that's why here's be 0, pi minus x, x sine y, and dy, okay? And you can evaluate this, okay? And you will get, it's actually negative x cosine y, evaluate at the 2 endpoints. Okay. So I will get negative x cosine pi minus x. And then minus the plus cosine 0. Cosine 0 is 1. Okay, this is a little bit more complicated than I thought. And plus x. Okay. Now cosine pi minus x is going to be negative cosine x. I hope you remember that. Okay. Cosine pi minus x is, first of all, when x is small, this is a negative number. Okay, it's a negative number. Okay, so now you have to evaluate this this integral, but this is a iterated. This is a This is, you have to use the integration by parts to evaluate this integral. Okay, the second one. Let's try this. Cosine x dx is going to be x d sine x. Okay, so that will be x sine x minus x sine x dx. So let me quickly finish that. It's cosine x. Okay, so this is an antiderivative function. Okay, then you go back to here. That will be x sine x cosine x plus half of x squared. Evaluate at 2 endpoints. Okay, when you plug them, sine pi, it's going to be 0. Cosine pi is -1. Okay, minus 0 cosine 0 plus 0. Okay, so that will be -1 plus half of pi squared minus 1. I should get pi squared over 2 minus 2. Anyway, this is answer. It's complicated a little bit more. So let's try another one. Let's try another way to evaluate this iterative double integrals. Okay, so let's see. This time I'm going to choose y variable. Okay, y start from 0 to pi dy. Okay, and that will be the x. So question is, what is the upper bound? Yeah, lower bound. I'm going to repeat this again. For each fixed y between 0 and pi, x is between 0 less than, this should be depends on y, so pi minus y. Okay. I think this is a bet. The reason is you don't need to use integration of parts. So you evaluate this integral with respect to x. That'll be half of x squared. Okay. So when so you get half of pi minus or even worse. Okay. So we have we get even more. Yeah. So you get a pi minus y squared. Okay. So this is a little bit more complicated because you have it's pi minus. You can use a substitution, change pi minus y squared to another variable, and you will still get the same answer, but a little bit more complicated. Let's use u to be pi minus u. Let u to be pi minus y. Okay. So when y is 0, I get the pi. When y is pi, I get 0. It's u squared. And then sine y is a sine pi minus u, but this one is a sine u. Okay, it's u, and the dy is going to be negative du. Okay, so you will get, wow. Now this is it's much more complicated. Okay, you have to get rid of u squared. So you still have to do integration by parts, but this choice of iterative integrals it's more complicated. Okay, u square sine u is going to be u square d negative cosine u. Okay, it's going to be negative u square cosine u plus minus cosine u and the 2u. Okay, then again, I have to do like this, u d sine u, right? Then you see, we have to apply the integral parts twice. Okay, then I differentiate that sine u. Okay, du. Okay, yes. Then I write down, this will be cosine u, so negative u square. Wow. Okay, plus 2 cosine u. So this is the antiderivative, unfortunately. Okay, this is antiderivative, and then they put back to the integrals. Okay, and half of, I hope we get the same answer. Okay, so it's 1/2. Plug 0. Let me write down the answer here. Plug 0. Plug pi for u. Cosine pi is going to be -1, so pi squared. Okay, and that will be 0. -2. Okay, that's the first part. But then I plug 0. That's 0, 0, and this will be 2. Okay, so what I got is pi squared over 2 minus 2. Do I get the same answer? Yes. I hope so. Pi squared over 2 minus 2. See, it's the same answer, but it's more complicated. Oh, so those are the double integrals. Yeah, Chubby integrals change it to double integrals. All right. I'm going to do one more problems. Okay, this is a problem number 12. You have this integral. Maybe I'm not going to evaluate, but at least I want to set up integrals. Okay, I is enclosed by the surfaces this time. Okay, there is 3 surfaces. Z equals x squared minus 1. Z equals 1 minus x squared. Y equals 0. And y equals 2. Wow. The question is, how do you draw this picture? I think first of all, we begin with xz plane. Okay. So x squared minus 1 is a parabola, opens upward. Z equals 1 minus x squared is a parabola, opens downward. Okay, this is they intersect at this point too. Okay, so the domain is xz plane. Then there's no restriction on, suppose there's no restriction on y, then in 3-dimensional space, how do you do that? So this is a x, that's a z, that's a y. Okay, so it's going to be like this. Okay, so this is a cross, this is a disk, right? If there's no restriction on y variable, what you get is you get kind of a cylinder type. Okay, right? No restriction, so no y, no restriction on the z. But we do have a restriction on the y. Y is between 0 and the 2. Okay, so y is between 0 and 2. So this is a part, yeah, this is a piece we got. Now, what is the best way to solve this problem? There are a couple ways to do. I'm going to set up 2 iterative integrals. Okay, I hope, but I'm not going to evaluate. Okay, you can do that. Maybe we don't have time yet. It's already 10:07. Okay, so this is a D. Okay, my D. Okay, the D is going to be xz in the xz plane. Okay, z is actually z is between 1 minus x squared and greater than x squared minus 1. Okay, this is between these two enclosed. Okay, that's z. So here's a d, right? This is d. So what I'm going to do is for each xz in the d, I'm going to use a horizontal lines, use a line parallel to the y-axis. Okay, I look at those lines. Okay, so their reference point is in the d. Okay, for each reference point in the d, I get a line parallel to the y-axis. So y variable along this line is between 0 and 2. Okay, it's a fixed. Okay, so the triple integral here, this
You're
will
saying
be,
that's 2 because y only goes from 0 to 2 in the bounds that they gave us, correct?
yeah, that's right. So this time, if we cut this cylinder in different way, then y depends on choice of xz. But here, y is perfect. It's just between 0 and 2. Okay, so it's going to be, first of all, the double integral. Okay, then y is between 0 and 2. Okay, x minus y dy and the dA. Okay, dA is actually dx dz. Okay, so this is the first one. Okay, after you evaluate this double integral, this single integral, so the single integral will be xy minus half of y squared, right? This is evaluate 2 endpoints. Then I get d, and I get 2x minus 2, I think. 2 squared over 2 is 2. Okay, so that is a dA. Okay, so now you just focus on this double integral. For this double integral, the best way to do is you use those vertical lines to write down the iterative integral, because x is between -1 and +1, and then for each x, z is between 1 minus x squared and greater than x squared minus 1. Okay, so this will be the integral from -1 to +1 dx, and the z is between x.
For the x bounds that you found, is that just doing the solving each equation for its
Yeah, that's
bounds
why
in
I
your
solved the
head?
equation. Yeah, that's right. That intersected those 2 points. Yeah, that's right. This is z equals x squared minus 1. This is equals 1 minus x squared. So that's 2 intersection points. So I solve them, and this is I'm not going to complete this integral. You know how to evaluate this integral step by step. Okay, and you get a polynomial x. Okay, so that's one way to do. Another way to do. Okay, let's go back to the picture. Okay, this is still the picture, right? Okay. All right, so this time, because the y variable for the points in the solid, the y variable between 0 and 2. So why not? I'm going to, this is the y variable. I'm going to, write down first single integral first with respect to y. Then this will be double integrals. The function x minus y and the dA. Okay, dA will be dx dz this time. So how can I determine this? This is supposed to be the domain with respect to y. Okay, different y depends on different domain. So, but as you can see, those cross section for the fixed y, this is a dy, they're all the same. Okay, so that means for each y between 0 and 2, okay, so we want to see how do we describe the dy, okay, and actually it's simple, it's still then x is between -1 and the +1, and the z is between x squared minus 1, 1 minus x squared, okay, 1 minus x squared, and x squared minus 1. Okay, so this is the same. It's nothing to do with the y. Okay, it's the same. So dy is just a d, the same d. Okay, this is the same d. So the integral okay, so the double integral, you have to evaluate this double integral first, and you end up with the same result. Okay, the double integral so will be also changed to the iterative integrals, -1 to +1, and the z is from x squared minus 1 to 1 minus x squared. Okay, that's it. So now it's nothing to do with the z. So x minus y, and the difference is 1 minus x squared minus x squared. So it's actually 2 minus 2x squared, I think. Yes. Okay. Yeah, 1 minus x squared minus, this will be 2 minus 2x squared. Okay. And then you get a polynomial of degree 3. Okay, you have to multiply this out and evaluate this integral. And finally, yeah, finally you can evaluate this Chubby integral. So I hope we can, when I have time to go over those problems, how do we set up this iterative integrals for the Chubby integrals. Okay, it's a little bit more complicated than the double integrals right now. Double integrals just 2-dimensional. Chubby integrals, you have more choices. Okay, and the first step is to express as like a double integral and a single integral. Okay, then double integral, you can take care of the double integrals later. Okay, when you finish the computation for the single integral. Okay. Okay, those are basically the two versions of integrals here. Two versions of iterative integral in the first step. Okay. Okay. And it depends on the solid. Okay. Then you look at the solid, you decide which way go first. Okay. If we ask you to write down two different iterative integrals, then you try in two different ways. Otherwise, just choose the best way, best iterative integral to evaluate the Chubby integral. Well, we will continue to study, but those students who did not do well on the double integrals on the test, please go to the section. I forgot, it's 15.2. There are several problems there. You should practice how to set up the iterative integrals, how to exchange the order of the iterative integrals. And those are the problems over there. Do more exercise when you have time. Okay.